My name's Robert Hawken, and today we're going to discuss the design of a scaled NASA Dragonfly capsule for radiation measurements in expansion tubes. This project will be done in conjunction with UniSC, the UQ Center of Hypersonics, and with help of Dr. Aaron Brandis, who is the current aerothermal lead for this NASA mission. Now, in 2028, NASA will be sending a 400-kilogram drone to survey Saturn's moon Titan for a 2034 arrival. Titan is the only moon in our solar system that has an atmosphere with up to 98% nitrogen and about 2% methane. This 4.5-meter capsule will hit Titan at over 27,000 kilometers an hour and will experience an unknown convective and radiative heating. Now, the problem here is that only one spacecraft has ever been sent to Titan, and that was in 2005, which only lasted 90 minutes. There is still a 60% uncertainty in the computational fluid dynamic modeling of this thermal radiation which the spacecraft will exhibit. This is because of the dissociation that happens in the molecules, as we have an example here of methane going from CH4 to carbon and 4 hydrogen. With that massive energy of entry, this superheats all of the molecules in the atmosphere until they vibrate apart into their atoms. Now here, the carbon will actually attach back to the nitrogen, creating CN molecules, which will vastly radiate to the spacecraft at an unknown amount. The aim of my thesis is to create a scale model of the Dragonfly capsule, which we can instrument with radiation spectroscopy optic fibers to measure the CN molecules of the capsule in the X2 tunnel. We'll be doing the experimental work in my PhD next year. This thesis is focusing on getting the experimental design and the model set up. My engineering process will be creating a scale model up about 90 millimeters to fit inside the X2 facility in Figure 3. I need to accommodate for the sting, which will hold the model in the flow and hold all of the optical fibers. I need to simulate Titan entry conditions at full scale and iterate over that capsule design so they both match. Now, my expected outcomes is that we're going to be able to replicate the Titan entry and also see at Figure 4. This is the current model, but we're not going to be able to use a setup like that for this model as we needed to measure the back as well. Now, the implications for NASA, looking at Figure 5 is my current model, which should be able to fit up the optical fiber housing for the NASA mission, and we can vary the methane and speeds throughout my PhD next year.